Paleoclimatic hypotheses suggest that approximately 750 million years ago, the Earth may have gone through a global glaciation known as the Cryogenic Period, in which all of the Earth's continents and oceans were covered by a thick layer of ice and reached an average temperature of minus 58 degrees Fahrenheit. These temperatures are the lowest that have been on Earth in all of history, and the factors that cause them could be present not only on our planet, but also on the planets closest to Earth. Considering the similarities that exist between Earth, Venus, and Mars, would it be possible that in the future, these two planets will suffer ice ages like those our planet suffered in the past? Can the conditions be met for the two planets closest to Earth to suffer global ice ages like the one Earth suffered millions of years ago? Join us on this journey of knowledge to find out. Snowball Earth. Snowball Earth is the hypothesis that suggests that the Earth experienced a series of global ice ages that covered most of the planet in ice. The defenders of this hypothesis maintain that it is not only the most extensive glaciation ever experienced by the Earth, but also the longest lasting. In addition, its impact on the biosphere would have been such that life was close to completely disappearing from the planet. Geological evidence suggests that during this period, ice sheets extended from the poles towards the equator, covering vast expanses of continents and oceans. The exact reasons behind these global glaciations are still being determined. Still, it is thought that they could be related to a combination of factors, including changes in solar radiation, the composition of the atmosphere, and interactions between the lithosphere and the biosphere. It is thought that one of the causes of this hypothetical great glaciation was the decrease in the levels of greenhouse gases. Curiously, these levels of greenhouse gases are the same as those currently on the planet. But 750 million years ago, the sun was 6% less bright, and therefore the Earth received less heat. It is known that if the natural cycles of glaciation and global warming continue, it is likely that in the future the Earth will once again go through a second ice age. Perhaps not as significant and long-lasting as the one 750 million years ago, but similar to the last, where the majority of giant mammals such as mammoths became extinct. Our planetary neighbors. Mars and Venus are the two closest planets to Earth. Although these two worlds have many similarities with our planet, they also have enormous differences, some of which are size. Earth has a diameter of 7,917.5 miles. Mars has a diameter of 4,212.3 miles, and Venus has a diameter of 7,521.8 miles. Mars is much smaller than Earth, having only 53.2% of the diameter of Earth, while Venus is very similar in size to our planet. Therefore, its gravitational force of attraction is similar to that of Earth. Gravity. Due to the differences in size, the mass of the three planets is also different, so the acceleration due to gravity experienced on the three planets is 9.8 meters squared on Earth, 3.7 meters squared on Mars, and 8.87 meters squared on Venus. That is, the force of gravitational attraction on Mars is only a third that of Earth, while on Venus it is slightly less than on our planet. This implies that on Mars it is much more challenging to have a dense atmosphere because gravity does not attract it with enough force, and it can be torn away by the solar wind. Magnetic field. As if that were not enough, Mars and Venus have small magnetic fields, which do not even represent 15% of that of Earth. For this reason, the solar wind and radiation mean that in these two worlds, there is a lot of harmful radiation for living beings, in addition to the fact that they are more vulnerable to what happens in space weather, and therefore their temperatures can vary significantly depending on whether the sun illuminates them or not. Temperatures. Finally, one of the aspects in which both planets differ most is their atmosphere and temperature. On Mars, they are more similar to Earth's, as the highest recorded surface temperature varies, but is generally around 68 degrees Fahrenheit in equatorial regions during the day. In contrast, the lowest temperature recorded on Mars is around minus 193 degrees Fahrenheit, These frigid temperatures are reached at night in the polar regions and higher elevations. In addition, it is thought that in the past, Mars may have had water ice glaciers like those on Earth, which were evaporated by solar radiation. However, although temperatures on Mars may be much colder than on Earth, they are much more hospitable to life than Venus, where the average temperature is 867.2 degrees Fahrenheit. But something interesting happens on Venus. At the top of the clouds, approximately 70 kilometers above the planet's surface, temperatures are minus 49 degrees Fahrenheit. The reason for this fascinating phenomena is that the temperatures on Venus are due to the greenhouse effect produced by the gases in its atmosphere. That is, if Venus lost its atmosphere, it would have much colder temperatures, especially in areas with no incidence of solar radiation like the poles. This means that, although it may seem crazy to think that the hottest planet of all could suffer a glaciation like the ones Earth has had, if a series of conditions arise, Venus could become an ice world without any problem. Snowball planets? Although Venus and Mars are very opposite planets, under exceptional circumstances, these two planets could become snowball worlds, as happened to Earth 750 million years ago. But how could that happen? Next, we will comment on the conditions that could cause such a phenomenon, but under no circumstances should it be understood that we are stating that this is going to happen. It's only a mental exercise of what could happen if these scenarios come together. Mars snowball. Let's start with the coldest planet of the two, Mars, which has a fragile atmosphere that is 100 times less dense than Earth's. However, it has gases such as water and nitrogen, which, under ideal conditions, could contribute to the decrease in its global temperatures. It is also known that the surface of Mars is covered with fine dust that produces storms very similar to sandstorms on Earth, except that there are no sandstorms on Mars, but there are dust storms. If we add the impact of a meteorite to these two factors, we would have the recipe for a large-scale glaciation. Mars is very close to the asteroid belt. In fact, it is known that many asteroids pass very close to the orbit of Mars, so it would not be unusual for one of these days one of the vast space rocks to collide with the red planet. When a meteorite hits a planet, depending on the size and speed, it can lift part of the crust and raise a lot of dust into the atmosphere, like when there is a volcanic eruption. If a meteorite fell on the surface of Mars, it would raise an immense amount of dust in the planet's atmosphere, leaving the entire surface in darkness. This would cause gases such as nitrogen and water vapor on the planet's surface also to disperse, and due to the lack of sunlight due to the darkening of the atmosphere, these gases would cool, turning into ice and falling on the planet's surface. This process would continue for several years until the surface of Mars is completely covered in ice, which would not melt or evaporate due to the low temperatures caused by the darkening of the atmosphere. Finally, after the dust cloud produced by the meteorite's impact dissipated, the atmosphere would clear, revealing a planet covered in a thin layer of ice, cold and white as a snowball. Due to the reflective property of ice, Mars would reflect sunlight more than it does now, contributing to it being even colder than it is today. In addition, at night, it would be brighter than Venus. Under this scenario, it would take several decades for the ice layer on the surface of Mars to dissipate, and during that time, the red planet would be a white snowball. Before we move on to Snowball Venus, be sure to stay tuned afterwards if you haven't seen our earlier release on the crazy prediction of a new ice age coming, Milankovitch cycles. What will this event cause to our planet? Snowball Venus. In the case of Venus, something simpler could happen. Venus is the only planet that rotates in the opposite direction to all the others. This means that while the other 7 planets, including Earth, rotate in one direction, Venus rotates in the opposite direction. Plus, Venus has the longest day of all. A day on Venus lasts more than 243 days, while a year lasts 225. This means that on Venus, a day lasts longer than a year. This drastic difference occurs because the dense atmosphere of Venus rotates in the opposite direction to the planet's rotation, which causes its rotation to slow down. This phenomenon is so strange and unusual that some scientists believe that the rotation of Venus will stop entirely and subsequently adjust to that of the rest of the planets. However, this process can take several million years. Because of this, there is a slight chance that Venus will have a tidal coupling with the Sun. Tidal coupling is when a celestial body always has the same face pointing towards another larger, more massive body. A typical example of tidal coupling is the Moon and the Earth. The Moon is tidally locked to the Earth, always showing the same face toward our planet. In the same way, if in the future Venus couples with the Sun, one of its sides will always point to the Sun. This would mean that one of the sides of Venus would always point to the Sun, and the other would always point towards the other side. In other words, one side of Venus would always be day while the other would always be night. If we add to this, as the years go by, the Sun will become brighter and will also give off more radiation. The lack of a magnetic field on Venus could cause the solar wind and the injections of coronal mass from the Sun to pluck off much of the atmosphere of Venus. If this happens for many years, little by little, Venus will run out of all the greenhouse gases that make its surface so hot. Suppose we mix both events, the loss of its atmosphere and the tidal coupling. Eventually, the side of Venus that points away from the Sun would gradually begin to cool until temperatures reach below zero. This would mean that Venus would become an eyeball Earth, a type of exoplanet whose rotation has been wholly synchronized with its star's rotation, so one side is always illuminated and the other is always in darkness. If this happened to Venus, the side facing the Sun would always be daytime and with extremely high temperatures. In contrast, the opposite side would be perpetually frozen and with extremely low temperatures. There would be the possibility that the intermediate zone between both sides, that is, the twilight zone, could have more stable temperatures, neither too hot nor too cold, where there could be even water and all the conditions to house living beings. An example of a planet that presents this peculiar situation is the exoplanet Kepler 1652b, a potential candidate for an eyeball world exoplanet since it is tidally coupled to its star. If Venus becomes this type of planet in the future, the eternal twilight region between the hot and cold zones could be warm enough to prevent water from freezing but cold enough so that it does not evaporate, forming a habitable climate zone where life could survive. While Venus couldn't become a snowball like Mars, it could become a planet where one side was permanently frozen. If Mars and Venus met all these conditions in the future, these two planets would look completely different than they do today. While one would become a snowball covered in ice and extremely low temperatures, the other would become an eyeball world, a planet in which one side would be eternally frozen and the other would always be under intense scorching heat with an intermediate zone where life could thrive. Remember, your opinion is the most important thing for us. Tell us, do you think these two planets could change so much in the future? Which of the two do you find more attractive? On Christmas Day, while people in Italy drink hot chocolate under their blankets, Brazilians are at the beach drinking some iced beverages. All of this could, however, change in the future. Imagine a world where the snow never stops falling, the cold never fades, and survival becomes a daily struggle. If a long winter period strikes the Earth, we would find ourselves in a post-apocalyptic state. Resource scarcity would be the first issue to hit us. The ground would freeze solid, crops would perish, and food would become scarce. To survive, we would need to choose between hoarding and sharing. Those who choose to hoard would become isolated and eventually come to ruin. Scientists think we might find ourselves in this situation in the years to come. There are cycles on Earth that are in conflict. Periods of hot weather alternate with cold ones. However, these conflicts won't last forever. In the future, the conflict will eventually stop and a long winter will come. But how do these cycles work? Join me to get to know more about it. Surrounded by cycles. Let's start by saying that here on Earth, we're basically surrounded by cycles. Let me explain. Our lives literally revolve around them, a series of events that are repeated regularly in the same order. There are hundreds of different types of cycles in our world and in the universe. Some are natural, such as the change of the seasons, annual animal migrations, or the circadian rhythms that govern our sleep patterns. Others are human-produced, like growing and harvesting crops, musical rhythms, or economic cycles. Every year on the 25th of December, the world celebrates Christmas Day. In the collective imagination, Christmas is made of snow and hot chocolate. This day is associated with snow and Santa riding his reindeer, bringing gifts and joy to all people, whether they're kids or adults. However, if you live in Brazil, you'll probably notice one thing. Christmas Day falls during summer. Many people like to go to the beach to tan. For the Brazilian people, there's no hot chocolate on Christmas. It would be crazy to even think about making one. You might want to eat an ice cream instead. The one and only reason why this happens is because of seasons. The cycle of seasons. You might already know why we have seasons, but I think it's worth reviewing, as this will serve as a starting point to understand the main topic of this video, the Milankovitch cycles. The reason why we have seasons is due to the revolution of Earth around the Sun and the inclined axis. As our planet orbits the Sun, the tilt of its axis causes different parts of the world to receive varying amounts of sunlight. This results in the changing of seasons in different parts of the world at different times of the year. During the summer, the hemisphere that is tilted towards the Sun receives more direct sunlight, resulting in longer days and warmer temperatures. Conversely, the hemisphere that is tilted away from the Sun experiences shorter days and cooler temperatures. This contrasting pattern is reversed during winter when the hemisphere tilted away from the Sun receives less direct sunlight, resulting in shorter days and cooler temperatures. Spring and fall are the transition seasons between summer and winter, and they occur when the Earth's axis is neither tilted towards nor away from the Sun. During these seasons, the amount of sunlight received is more evenly distributed across the Earth, resulting in moderate temperatures and more balanced weather patterns. Seasons have a significant impact on life on Earth. Plants and animals have adapted to the changing climate, using cues such as temperature and day length to regulate their life cycles. Many animals migrate to warmer climates during the winter months, and some plants only flower during certain seasons. In addition to its impact on the natural world, seasons also affect human activities. Seasonal changes can influence everything from our moods and behavior to the economy. For example, winter sports and activities are popular in places where it snows, while beach activities are more prevalent in places with warmer climates. As you can see, seasons are an important cycle that repeats regularly, with each season bringing new growth and changes to the natural world. All over the course of 1 year, periods of warm weather alternate to colder ones. The Milankovitch cycles. So the presence of seasons is due to the particular configuration of a planet's axial tilt with respect to its orbiting plane around the host star. But as the Serbian scientist Milankovitch pointed out a century ago, this is not the only factor capable of having an impact on Earth's weather and climate. This genius hypothesized that the long-term collective effects of changes in Earth's position relative to the Sun are a strong driver of Earth's long-term climate and are responsible for triggering the beginning and end of glaciation periods, ice ages. Did I already mention this guy was a genius? He knew very well that the orbit of a planet is described by what aerospace engineers call the orbital elements. These are 6 important quantities that help describe the movement of an object around another object, whether it is an artificial satellite like the JWST around the Earth or a star around the black hole at the center of our galaxy. He first asked himself what would happen to the Earth if one of these elements, the so-called eccentricity, slowly changed over time. Changes in eccentricity. The eccentricity gives information about the shape of an orbit. When it is 0, the orbit is a circle. The more you depart from 0, the more stretched and elliptic your orbit is. The thing is, due to the gravitational perturbations of Saturn and Jupiter and other minor factors, the Earth's eccentricity, which is quite low, can vary over time, changing the shape of Earth's orbit around the Sun. This in turn affects the distance between the two bodies. Eccentricity is the reason why our seasons are slightly different lengths, with summers in the Northern Hemisphere currently about 4.5 days longer than winters, and springs about 3 days longer than autumns. As eccentricity decreases, the length of our seasons gradually evens out. What Milankovitch did was to examine how these variations affect how much solar radiation reaches the top of Earth's atmosphere, as well as where this radiation reaches. He found out that when the Earth's orbit is at its most elliptic, about 23% more incoming solar radiation reaches Earth at our planet's closest approach to the Sun each year than it does at its farthest departure from the Sun. Currently, Earth's eccentricity is near its least elliptic, most circular, and is very slowly decreasing, in a cycle that spans about 100,000 years. However, the change in global annual insolation due to the eccentricity cycle is very small. Because variation in Earth's eccentricity are fairly small, they are a relatively minor factor in annual seasonal climate variations. Changes in obliquity. But that's not the end of it. This genius, Milankovitch, also took into account something else: the obliquity and axial precession. The obliquity is the angle between the plane of the Earth's orbit and that of the Earth's equator. This tilt has varied between 22.1 and 24.5 degrees over the last million years. The greater the tilt, the more extreme our seasons are. Think scorching hot summers and bone-chilling winters. Interestingly enough, a larger tilt angle actually leads to periods of deglaciation. So basically, more tilt equals more melting and retreat of glaciers and ice sheets. But this effect isn't uniform worldwide. Higher latitudes experience a greater change in total solar radiation than areas near the equator. Currently, Earth's axis is tilted about halfway between its extremes at 23.4 degrees. And get this, that tilt angle is slowly decreasing in a cycle that lasts about 41,000 years. With his calculations, Milankovitch found out that while our winters will gradually become warmer and our summers cooler, snow and ice will begin to build up in high latitudes. This leads to large ice sheets reflecting more of the sun's energy back into space, which, you guessed it, promotes even further cooling. Axial precession. For what concerns axial precession, let me first explain what it is. I don't know if you're aware of this, but the Earth wobbles slightly on its axis like a spinning toy top. This wobble, caused by tidal forces from the Sun and Moon, affects Earth's rotation and is known as axial precession. This cycle lasts about 27.7 thousand years and makes seasonal differences more extreme in one hemisphere and less extreme in the other. Currently, perihelion, Earth's closest point to the Sun, occurs during winter in the northern hemisphere and summer in the southern hemisphere. But in about 13,000 years, this will switch, causing the northern hemisphere to experience more extreme solar radiation and the southern hemisphere to have more moderate seasons. There's also apsidal precession, where Earth's entire orbital ellipse wobbles due to interactions with Jupiter and Saturn. This cycle lasts about 112,000 years and changes Earth's orbit orientation relative to the elliptical plane. Combined axial and apsidal precession have an overall precession cycle lasting about 23,000 years on average. And fun fact, Earth's North Star changes over time, with Polaris and Polaris Australis being the current stars. But a few thousand years ago, it was Kochab and Percab. Milankovitch's crazy prediction. The small changes set in motion by Milankovitch cycles operate separately and together to influence Earth's climate over very long time spans, leading to larger changes in our climate over tens of thousands to hundreds of thousands of years. Still, what he found is both very interesting and scary. At some point, we, the Earth, will eventually be experiencing another ice age. The two main assumptions posed by Milankovitch were: 1. That the changes in radiation at some latitudes and in some seasons are more important than others. 2. That the obliquity is the most important of the three cycles for the climate. Putting these into his own mathematical model, he calculated that ice ages occur approximately every 41,000 years. Given that the last ice age we know of happened roughly 20,000 years ago, this would in turn mean that the next ice age will be happening in 20,000 years or so. However, subsequent research confirmed that ice ages did occur at 41,000-year intervals between 1 and 3 million years ago. But about 800,000 years ago, the cycle of the ice ages lengthened to 100,000 years, matching Earth's eccentricity cycle. While various theories have been proposed to explain this transition, scientists do not yet have a clear answer. This problem is also known as the transition problem. In any case, according to the most recent astronomical measurements, there won't be a new ice age before 50 to 100,000 years. Predictions accuracy. Making predictions when it comes to long-term climate on planet Earth is no picnic. In principle, a good estimate of the variations of the orbital elements over time would make everything easy if we only had a good model linking these variations to climate variations. However, the orbital forcing mechanism that acts on the climate is still not completely understood. Currently, we lack a good model that expresses the climate changes in the function of the orbital ones. Due to these reasons, research to better understand the mechanisms that cause changes in Earth's rotation and how specifically Milankovitch cycles combine to affect climate is still ongoing. But the theory that they drive the timing of glacial interglacial cycles is well accepted. That's all for this video. Thank you so much for watching. What would you like to hear next? Let us know in the comments below. See you next time on the channel.